We're going to talk about harmonic oscillator. I'm not going. Almost everything that I'll teach is going to be also in these documents. However, I will teach a little differently than those documents. I don't know how much you're used to looking at them, but whatever. Harmonic oscillator. For now, you can ignore the documents. We're not there yet. So, you know that in general for harmonic oscillator, we can say that the energy is potential energy plus kinetic energy, which is half kx squared plus half v squared. Right? That's what we used to say in the past. However, now we're going to write it in a different way. We're going to say that it is half m omega squared x squared plus p squared over 2m. Why is that? Well, you already know that I can write the kinetic energy as such, and it's just more convenient because p is our momentum, it's our momentum operator, etc. We wish to move from this representation to this representation. They're completely, like, they're the same. There's no meaning of writing this or this, where omega is the square root of k over m. Simply, this is more convenient because the letter k is taken. And as you know, there aren't enough letters in the alphabet, right? T is time, T is tension, T is lots of other things. So k is momentum, and k is also the constant of the spring. And spring can be the thing between winter and summer, and spring is also a thing of water. So we don't want to confuse ourselves so much. So you're going to use this representation, and this is another potential where v of x is half m squared x squared, and it's another potential that we did not learn about yet. So far we spoke about potential that were quite either zero, or we had a well, or we had a barrier, or we had an infinite barrier, or we had a delta. This is a delta, whatever. Or we had a delta. We had all these potentials. They're all very sharp. Now we're going to talk about this potential. It's very different. Why are we so interested in the harmonic oscillator? Well, first, just part of the course. Secondly, it's us physicists, we like to compare any problem to stuff that we know, and everything that we don't know, we just say it's a harmonic oscillator. You have a molecule of water with H2O, so you have H and H, and then an O. Oh, let's just say that you have here two protons, thank you. Protons and two electrons that are here, and they're oscillating. Okay? We have the sun and the earth. Let's just say that it's like a harmonic oscillator. It's not. What do we care? This is something that we can understand. So everything we don't understand, we map to something that we can solve, and this is one of the only potentials that we can fully solve. That's why they're very important.
And any potential to second order is a harmonic oscillator.
Exactly. Any potential to second order is a harmonic oscillator, which is why we like it. So there is a question in sometimes if we, whatever. That's it. So what is the solution of that thing? As we saw in the lecture, it is the Hermite polynomials. But before we do this, let us do a few mathematical steps to make it a little nicer. Well, what I'm going to do, let's write h psi is equal to e psi. This is a time-independent Schrödinger equation. Therefore, half m omega squared x squared psi plus, what is p squared? P squared is minus h squared over 2m. The derivative. Therefore, I can write here plus, or this is plus will become a minus h squared over 2m psi double prime is equal to e psi. Let's move this here and this here. And let's use papers because I don't like getting confused too much. And we're going to write that psi double prime plus 2me over h bar squared minus m omega squared over h bar x squared psi is equal to 0. Now what I should have done is, instead of calling it psi, I should have called it phi all along. And then I can say that the solution of the time-dependent Schrodinger equation would be psi is a sum over Cn, Pn e to the minus I Ent over h bar. That's what we always say, right? So you first solve phi is a function of x, psi is a function of xt, and this is the full solution of the Schrodinger equation. The only time is that I did not solve this thing, right? So now we're going to define something that's going to stay with us for a while, which is sigma x, which will be, wait a second, that mistakes? I think this is a mistake here. What? Did I miss an m?
Match the equation.
It's possible I did. Yeah, here there's an m squared.
Yes.
Thank you. Do you have also these papers?
No.
So let's define here sigma x, which will be this, and sigma p, which will be square root of m omega h bar. Now, what is the dimension of sigma x? Sigma x is angular momentum, which is kilogram times the meter squared over second. This is angular momentum divided by m omega, which is kilogram over second. Hey, this is exactly meter. This makes me happy because that's what I wanted. That's why I call it sigma x, because it has dimensions of meters. Let's look at sigma p. What are the dimensions of sigma p? It is square root of kilograms over second times h bar, which is kilogram times meter squared over second. Hey, I got kilogram times velocity. I got momentum. MV. Good, so I'm happy. This is sigma x and sigma p. And now I wish to write this equation in the language of sigma x. I hate this whiteboard. Okay. Well, h bar over m omega. I have here h bar over m. I won't really change the variables. I'm just gonna copy to my paper. I'm gonna have here phi double prime plus 2 over m omega squared sigma x to the fourth times en minus x squared over sigma x to the power of 4 times Pn is equal to 0. Well, I see that here it's true because I want the h bar to be on the bottom and the m omega to be on the top, and I want it to be the power of 2. If I do sigma x to the power of 2, I get it without the square root. To the power of 4, I get exactly this. Let's see if it's true to the other one. The 2 and the e stayed here. So I said that m over h bar squared is equal to 1 over m omega squared times sigma x squared, which is h bar squared over m squared omega squared. Is this true? Yes, it works. Okay, so I showed you that this translation works. And the solution now reads that phi n of x is equal to 1 over square root of, this is going to be scary, 2 to the power of n squared, n factorial, square root of pi, times 1 over square root of sigma x, times hn of sigma over sigma x, times e to the power of minus x squared over 2 sigma x squared. Oh no, where the energies are given by h bar omega n plus 1/2, where the n's are 0, 1, 2. Reminder, energies of infinite potential well are en are pi squared h bar squared n squared over 2m n squared, where n starts from 1, 2, 3. Okay. So, we're going to spend the next, I don't know, half hour at least, talking about Hermite polynomials. What you need to know, but first, okay. Okay, what can we say about it? First, these things are not very transparent. I don't really know how they're going to look like. It's a disgusting function. As opposed to lots of other wave functions that you've seen, like a wave function, like sines. This one is not really transparent, right? I can say that it's going to be either even or odd, because the potential is even. I see that there is a certain number, a normalization, that has to do both with the energy level n and with sigma x, where sigma x is again related to the energy. It's related to the energy through omega, and omega is here. And then here I have this, which is a polynomial, times an exponent. What can I say about this exponent? I can see, first of all, that it goes like e to the minus x squared. When I had the tunneling problem, when I had this, when I had an energy coming here, so we saw that here I'm decaying exponentially, right? E to the minus x. Here I'm going like e to the minus x squared. Why is that? Because the more I try to go here, if I try to penetrate through, if I try to tunnel, the more I go, the higher the potential gets. It's harder to go through. That's why I get a stronger decay. Okay. As I said here, it's a very stupid point to get confused on, but it's very natural to get confused on. The energy here starts from 0, 1, 2, and here the energy starts from 1, 2, 3. Why is that? Well, it just is. The energies were sine of n pi x over L in the infinite potential well. For n equals 0, you'd get no particle. Here, for n equals 0, I still get something. 0 factorial is 1. H0 is, I think, number. I don't remember what it is. You probably do. We'll see it soon. What is H0? I think it's 1. So this is still a number. I still get something. It's just an exponential. Gaussian, actually. So I still get a particle here at n equals 0. What else do I want to say about it? I want to just show you what will be a very low energy level and a very high energy level, and how does it correspond to the classical limit. Where n equals 0, what I get is a Gaussian. So I have a high chance of finding it here and a low chance of finding it here, right? Classically speaking, where would the particle be at a very low energy?
In the center.
It would just simply be here without moving. This is of course not possible in quantum mechanics, because if you know the velocity is 0, then the particle should be everywhere. It cannot be everywhere because we have a barrier, we have a well. Therefore, this is of course not possible, but still I see that the highest chance of finding the particle is exactly in the middle, right? Let's talk about the, this looks like an H. N is equal to 1 million, whatever. What happens here? I would get here a wave function that looks like this. And of course here a decay. Why is that? It makes a lot of sense. If I have a classical particle going back and forth, where's the lowest chance of finding the particle? In the middle. Why so? Because if you go like this, you're the fastest where you're in the bottom. So if you just stop, if you freeze the picture at any given time, there's a higher chance of finding the particle here where it's slow than finding it in the middle where it's fast. That's why when I'm a classical particle, so I can just look at it this way, I can't even see the difference between this and this, because my measuring tool doesn't differentiate between these two already.
It's like a roller coaster, right?
Yeah. Just like our lives. So here we're slower, and that's why there's a higher chance of finding the particle here. Okay. Now we're going to talk about the Hermite polynomials. It's going to be fun. I'm going to start with the Hermite polynomials, and then towards the end I'm going to talk about lateral operators. Lateral operators are much more fun to deal with than the actual functions. The Hermite polynomials come from a differential equation, not exactly this one. How do I know that it's not exactly this one? Because this one, the solution of this one is not the Hermite polynomial, it's something else. The Hermite polynomial is time to a certain exponent. The Hermite polynomials are the solution of h n double prime minus 2x h n prime plus 2n hn is equal to 0. h0 is going to be 1. h1 is 2x. h3 is 4x squared minus 2. h1 is h2. h3 is 8x cubed minus 12x, and this seems very, very random. You do notice a pattern that every level has a higher level of a polynomial, x to the power of 0, x to the power of 1, x to the power of 2, but you have very, very random numbers that you would not have guessed. Have you seen these in class? With Richard? Not at all. Okay. Orthogonality. The orthogonality of Hermite polynomials is defined with a weight function. The integral from minus infinity to infinity of hm of x, hn of x times e to the minus x squared dx is going to be square root of pi 2 to the power of n factorial delta of nm. So this is something that one needs to remember. We use orthogonality to be without a weight function. You could have a constant. It doesn't really tell exactly 1. You need to have 1 over square root of pi. This we're used to from sines and cosines or something. So here you have a weight function and you have a certain number. Does this number here ring a bell?
Yes.
It's here what we divide by. This way, if I do psi squared, wait a second, look at that.
That's why the exponent is also there.
You can also see this exponent and this exponent, they're not exactly the same. What's the difference? There's a 2 here, right?
Which is you have to square the...
Exactly, because you have to square the wave function. Do you all see that? Let's try it more explicitly. I want to define here y as x over sigma x. Okay? And y tilde as x tilde over sigma x. Sigma x has to do with the potential. It's not a function of x. It's the same sigma x. So phi n of x, phi m of... What did I want to do now? No tilde, sorry. Phi n of x, phi m of x. I want it to be 1, right? I want it to be delta nm. Is this what we get? Well, I get here 1 over, I have this for n and this for m. So square root of 2 to the power of n plus m, pi, I have pi from each one, times, okay, dy is dx over sigma x. So this cancels out this thing.
You're missing the n and the n factorial, right?
Well, yeah, I know. Now the n factorial needs to be also inside a square root, right? So here, n factorial, n factorial. Now I can get, now all I have left is the h and the exponents, right? h m of y, h n of y, e to the power of minus y squared. That's it. Of course, I forgot to write dy in the integral.
And divided by sigma.
No, because this is by the dy and the dx.
Right.
And this here gives me exactly, wait a second, let's see if it works. Square root of pi, I get here, well, this is just a constant, right? So I get here square root of 2 to the power of n plus m, but it's going to be, if n is equal to m, I'm going to have here a delta in m, okay? Since I'm going to have a delta in m, square root of pi, 2 to the power of n factorial delta in m, which comes from this integral. And from here I get the exact same thing. That's the square root of pi stays square root of pi, but the two other things I don't have a square root of anymore, so I have n factorial, 2 to the power of n, and that's it. So it works. So I showed you what the orthogonality is, and now I want to show you the generating function. Function יוצרת in Hebrew. It will be hn of x will be minus 1 to the power of n e to the x squared ddx to the power of n e to the minus x squared. Relatively simple term. I'm going to do the derivative of this n times. And after I do this, of course, these two exponents will cancel each other out. And I'll be left with the polynomial. Let's show what happens. h0 of x will be the derivative of 0 times. It's going to be minus 1 to the power of 0 e to the x squared e to the minus x squared, which will give me 1. Heh? This is indeed h0 of x. h1 of x will be minus 1 to the power of 1 e to the x squared. If I do the derivative of this, it gives me minus 2x, right? Minus 2x times e to the minus x squared, which gives me altogether 2x. Because the minus of this and the minus of that becomes a plus. Should we do one more, or was that enough? I think that was enough. Okay. Now we're going to prove and show different things about Hermite polynomial. This will show you the kind of games I will ask you about in the homework, I think. Prove that hn of x is equal to 2x minus ddx to the power of n on 1. This is weird. What?
Just the ladder operator, right?
It has to do with the ladder operator, but so you're saying it's like it has to do with the ladder operator, but not in a transparent way. I don't see exactly how. So, how do I even show this? So, let's start with this thing. Okay? Sorry, with this thing. I'm going to multiply both sides from the left by I'm going to multiply both sides. I don't know how to plan my whiteboard. And right here, minus 1 to the power of n e to the x squared ddx to the power of n e to the minus x squared is equal to hn of x. And now I'm going to multiply both sides by minus 1 to the power of n e to the minus x squared. Okay? So, what I get on the left hand side is minus 1 to the power of n minus 1 times e to the minus x squared hn of x is equal to the derivative x times n times of dx n times to e to the minus x squared. Wait a second. Okay. I'm remembering what I wanted to do. All the n's here, I want to turn them to be n minus 1s. I'm allowed to do that. So also here, I'm going to have n minus 1 and n minus 1. Now let's do ddx to both sides. Let's derive both once from the left. So here I'm going to have the derivative of this and the derivative of that, right? I'm going to have minus 1 to the power of n minus 1, the derivative of this times that plus the derivative plus this times the derivative of that. So I get here minus 2x h n minus 1 of x plus h n minus 1 prime of x times e to the minus x squared. This is the left hand side. This is equal to d dx n times on e to the minus x squared. Okay. Now let's multiply again both sides by minus 1 to the power of n e to the x squared. Is this too fast? Is this too technical? Is this too boring? It is a little boring. It's very technical. Okay. I'm basically recognizing now that this, I started with hn minus 1. I moved stuff to the left, I derived both sides, and now I want to move back up to hn of x. This is not very different than hn of x. All I need to do is multiply both sides by this. So now I'm going to have minus 1 to the power of n d dx to the power of, on the right hand side, minus 1 to the power of n e to the x squared d dx to the power of n e to the minus x squared, which is exactly hn of x. This is what I have on the right hand. And it's equal to what happens when I multiply this by that. Here and here I'm simply left with a minus. So I have a minus. The exponent in the exponent, this and this cancel each other out, and I have minus 2x hn minus 1 of x plus hn minus 1 of x. This one has a prime on it. Did you understand how this and this cancel each other out? Here there's no derivative of this, it's just a multiplication. Okay. Minus and minus makes a plus. It gets that hn of x is 2x hn minus 1 plus hn minus 1 prime. Ooh, wait a second. This I can even put a nice thing around because we're going to use it again. But this gives me a general relationship between Hermite polynomial and the one lower than it. I can even check it on 1 and 2x, right? We saw that h1 of x is 2x and h0 of x is 1. Does it work? This would be 0. 2x 1 is equal to 2x. Now, this was once, right? What happens if I activate it again? I can rewrite it. I can rewrite this thing and write hn of x is equal to 2x minus d dx over h and minus 1 of x. Wait a second, so maybe hn of x is going to be 2x minus d dx times 2x minus d dx over h and minus 2 of x. This is just doing one more step in the recursion. And from here I get the general thing I wanted to prove that is not written here anywhere anymore. Okay, I can write here that hn of x is equal to 2x minus d dx and times over h0 of x, right? What is h0 of x? 1. Now, as Maxime said, all these relationships we're seeing between H and Hn and the one right next to H, right, one above or one lower, has to do with the ladder operators. Now we're going to show another identity. Okay, write it. May I erase this? Okay, I'm not erasing these things on the top because I'm planning on using them again. But I will do this, so it's a little clearer. Let's prove that Hn prime is equal to 2n times h n minus 1. Let's do the derivative of, let's do the previous thing, based ourselves on the thing we just proved. Hn prime, what did we just show before? We saw that ddx of Hn is ddx of whatever it is of Hn minus 1, right? 2x minus ddx of Hn minus 1. I used the thing we just showed a second ago. This is when I do the derivative of, well, I have the derivative of 2. When I do the derivative of dx, I have 2 times h n minus 1. If I do the derivative of this times that, plus when this multiplies the derivative of that, I have plus 2x h n minus 1 prime minus h n minus 1 double prime. Now I had I have this thing. What is this?
The Hermite differential equation.
This is the original Hermite differential equation. So I can see here that 2x Hn prime is equal to Hn double prime plus 2n Hn, right? Let's use the n minus 1 version of this thing. Hn minus 1 double prime plus 2 n minus 1 h n minus 1 is equal to 2x h n minus 1 prime. Wherever it said n, I replace it with n minus 1. Here I have 2x h n minus 1 prime. I have exactly this. I can replace it with that. Now I can say that Hn prime, which is this, is equal to 2h n minus 1 coming from here plus 2x hn minus 1, which is this. Have your hn minus 1 double prime plus 2 n minus 1 hn minus 1 minus hn minus 1 double prime. So this here is this. And this thing is this thing, which is this thing, and became this thing. Oh, wait a second. This and this are the same. And this, 2hn minus 1 minus 2h and minus 1 also cancel each other out. So this dies with this. What am I left with? hn prime is equal to 2n h n minus 1. Plus 60 seconds of breathing time for you guys. Meanwhile, Kai is going to tell us about his week. No? Okay. I find like hearing the same person for an hour and a half straight to be annoying, even if it's a great teacher, theoretically. Oh, do you know the Element song by what's his name? Thomas Lehrer? Okay, we're gonna. Come on.
Of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. Try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, tartanium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bilzboron, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium, phosphorus and francium and fluorine and terbium, manganese and mercantile, lead and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium, berkelium, and also metallium, einsteinium, nobelium, and argon. Those days. Life was much simpler in those days. Which is due to Aristotle, and which goes like this. There's earth and air and fire and water.
Anyway, so now I want to show you what would be find x for any psi of x. Now we're leaving the Hermite polynomials. We're going to get back to them soon, don't worry. And I'm asking you about psi, going back to quantum mechanics, going back to harmonic oscillator. What would be psi of x? The mean the mean of the location. How would you find it? Well, you know that in general, psi of x t is a summation over cn's times pn of x e to the minus I ent over h bar. Instead of ent over h bar, I'm going to write omega n. So this is psi. Now I want to write now the integral from minus infinity to infinity of psi complex conjugate times x times psi, right? Dx. This is going to be nasty. Enjoy. This is equal to the integral from minus infinity to infinity, and I want to take the summation of the complex conjugates. Let's call it n. Sum over cn complex conjugate phi n complex of x e to the plus I e n t over h bar. This is psi times x. times another psi. Now here I need to take another summation. It needs to be another index because I need to take all the possible combinations, right? So sum of m, cm, phi m of x e to the minus I emt over h bar, and then I need to do all this integral dx. Fun, right? Now we're physicists, so we're allowed to change the order of integration and summation. Let's move all the summation to the left-hand side. I get here sum over m, cn complex cm, e to the I omega n minus omega m t, the integral from minus infinity to infinity over phi n. The complex conjugate is meaningless because it is a real function. So phi n of x times phi m of x. Now remember what is those phi n's, right? Let's call this thing I. And this is the integral that I wish to solve now. What is this integral? I is it is a disgusting constant. 1 over 2 to the power of n plus m. N factorial, m factorial, pi. Times sigma x. Now I need to take that integral. I'm going to replace variables to y, okay? Again, y is going to be x over sigma x. Hm of y, hn of y, e to the minus y squared times y dy. And of course, when I replace the variables to y, it also gets rid of this. How do you solve this thing? Does it remind you of something? Or trigonometric relations where I had h and an exponent. What's bothering me?
The y.
The y. Do you know of any way of getting rid of this y?
With the Feynman.
We just showed it before. We saw before that 2y times hn minus 1 is equal to hn plus 2 times n minus 1 hn minus 2. It's one of the things we showed before. Let's move it up a level, okay? 2y hn is going to be hn plus 1 plus, wait a second, what am I doing here? Yes, plus 2n hn minus 1. Now I'm going to plug this in here instead of one of them, right?
You can also spread it into cases, right? For example,
Yes.
if they are pair, even or odd.
I can. You mean for ends?
Right, m and n's, you say m is even, n is even.
If they're both even, if they're both odd, etc.
Right,
I could. How would it help me?
because you know that
I'm saying-
integration.
I'm saying sometimes we'll get a case from 0 to infinity. I can replace it with an integral from 0 to infinity, and then what?
No, but you see, you have an odd function.
I'm saying when it's odd. Oh, you're saying this thing.
Yes, and all the left part is even, so it's 0. right?
Unless one of them is
Right.
odd.
Unless one, and you would only have to
If
solve
one is
that
odd and the other
case.
is even, so you still have an infinite. You still have infinity cases.
Right, but
Yes.
I think you can go with that solution because you know that, and then you can make the substitution that you are making.
Mm-hmm. Okay, you could do that.
I know.
Okay. I don't know if I should trust this. I probably should. Because here there's another sigma x. It says here that there is a sigma x on the numerator. Yes, there is. They're right. Because here there was an x because of this thing. When I write y instead of x, I need to multiply by sigma x. Now I get a new integral. I is going to be sigma x divided by the disgusting square root 2 to the power of n plus m, n factorial pi times integral from minus infinity to infinity over. Now I wish to replace this one, whatever, one of them, with this thing. So I will have here half, y hn is equal to hn plus 1 divided by 2 plus n hn minus 1. I have here half of hn plus 1 plus n hn minus 1 times hm times e to the minus y squared dy. As you see, I have a relationship between neo neighbors. hm and hn minus 1 are going to be delta. I'm going to get here at the end delta of m n minus 1 or delta of m n plus 1, which is what I expect if I've ever heard of ladder operators. So I get here sigma x over square root of 2 to the power of n plus m, n factorial pi times half of delta n m plus n delta n m, right? Is that it? Not exactly, because I also have what I get here from the delta. The delta is also times something, right? It's times 2 to the power of m factorial, and I think there might be a square root of pi happening here, no? Wait a second. I need to look again at the orthogonality. 2 to the power of m factorial. Delta, yeah, there should be also a square root of pi here, right? Okay. And I get here to a term. Now I need to plug this back to what I had before with the exponents and stuff, right? All this was the integral I. What I wrote here is the solution of the integral. I need to multiply by these summations, right? Cn, Cm, e to the I, omega n minus omega n times t. Right? I still have that. And then I get the mean expectation value for any psi. And what I get here I'm going to just write the final line. Sorry for the messy whiteboard. It's just not the whiteboard not big enough for all these long stuff. I get here that x is sigma x over 2 times sum over Cn. I can write here complex because it might be complex. Times square root of n plus 1. I have here, wait a second, yeah. I have here square root of do you agree with this? אני טועה? רגע, אמרתי הפוך? Yes. אמרתי הפוך. Good. Okay, so I have here 2 to the power of m, and I have here 2 to the power of n plus m. Wait a second, is this what I want to do now? a second. It's coming from this square root of. No, sorry. It's coming from the factorial. I have here m factorial divided by m factorial times n factorial. But m might be n minus 1, n plus 1, which gives me this thing. C n plus 1 e to the minus I omega t plus square root of n c n minus 1 e to the I omega t. What was the point of this? Just to show you the kind of questions where you could use all the Hermite polynomials back in quantum mechanics. Because I started with the potential, I moved to telling you Hermite polynomials are not the solution, they're part of the solution. Then we spent 45 minutes learning about stuff with Hermite polynomials, and I wanted to show you a case where I can show it to you. Now I did the math a little fast. I might have gotten mistaken about the constant here and there, but the point was to show you an example where I could use these relations. And come here to the ladder operators. We love ladder operators. Then have you watched the Big Bang Theory series? Yeah? Have you heard of the TV show called Big Bang Theory?
Oh yeah.
So the main actor.
I'm on season 7 right now.
So there's a point in which the main character, Sheldon,
Yeah.
needs to sing this. And the actor said this was the hardest part of the whole show.
Yeah, I saw the interview. That he was like a torture for him.
Yeah. And there's the actor of Harry Potter, Daniel Radcliffe, also sang this once in an interview, the whole thing. I think even reading it from the paper is very hard. I'm talking about singing it without a paper and playing music meanwhile. You wonder if I do this full time, how long will it take me to be able to do that? Like a year? I don't know how to play the piano, so I guess more. Let's start now with classical mechanics. We know that in general, the energy of a harmonic oscillator is p squared over 2m plus half m omega squared x squared. Now I'm leaving the Hermite polynomials. I'm starting to attack the whole problem from the beginning with another angle. This is the energy in a classical mechanics. Can I write this also in another way? I'm going to write it now. E is equal to 1 over 2m times m omega x minus ip times m omega x plus ip. What do I get here? M, you know, a plus b, a minus b is a squared minus b squared. But if I put an I here, so I get this. So I get here m omega squared x squared divided by 2m. But when the m is also squared, I get exactly this. And for the second term, I get here p squared over 2m. So this works. What happens if I try using it for operators? Let's see what is m omega x operator minus ip m omega x plus ip. Well, I would have this times this, which is divide everything by 2m, yes. 1 over 2m. We'll get 1 over 2m times m omega squared x squared plus p squared over 2m. So far so good. Now I would have this times this, which is plus I plus I m omega. Now when I do this times this, I have xp. When I do this times that, I have again I m omega, but minus px. Wait a second, I know what this is. This is IH bar, right? So if you are IH bar, altogether I get that, well, this is 1 over 2m times m omega squared x squared plus p squared over 2m plus I and I can't, gets me minus. I get minus m omega h bar. But everything was divided by 2 m's, right? Also this needs to be divided by 2 m's. I get here minus h bar omega over 2. This was, I think, the easiest way to get to ladder operators. Is this clear? Because ladder operators are weird. So far you've seen operators, only operators that represented real physical values, location, momentum, energy. Not suddenly we're going to use operators that are not real, and their eigenvalues are not necessarily, like you won't be able to measure exactly a degio. What is a degio? So what this is going to be, you know, it's a superposition of x and p. You can't measure the location plus momentum. What is this? What are the units of this thing? So, do you agree to what I wrote here? Now, I want to say this at the end of the day. Wait a second, I did not need this here, because I use it here.
You have to
I did some math.
divide the second term, only the second term.
This thing. Like, now it's good. Oh, here.
Right.
And also this one needs to have a half on it, right? So, this at the end of the day is my Hamiltonian, right? What I wrote here is 1 over 2m times m omega x minus ip m omega x plus ip is equal to this. So now all I want to do is isolate this, because this is my real Hamiltonian. So I want to move this to this side. So I can conclude and say that h, which is m omega squared x squared over 2 plus p squared over 2m is equal to this thing, m omega x minus ip m omega x plus ip divided by 2m plus h bar omega over 2. This, as you know, is going to be the ground level of the harmonic oscillator. Now we're going to use again this definition of sigma x and sigma p. And we shall define A as, what is this? This is a mistake. Wait. Wait, what? There's a mistake here. That's not good. Oh, no, it's not a mistake. It's just typo, whatever. I have here x over square root of 2 sigma x plus I p over square root of 2 sigma p. And a dagger will be the same thing, only with a minus in between them. he asked me for what are the dimensions of this, and of course the dimensions are 1, sigma x is meters, and sigma p is momentum. So p divided by sigma p is dimensionless, x divided by sigma x is dimensionless. So I have these two things, and this is basically a Degel. This is basically A, and therefore my Hamiltonian is now h bar omega times A Degel A plus 1/2. And isn't this nice? If you take h bar, do you want me to work on the constants here, or you trust each other me enough? Would it make you feel better if you actually see it? No. Okay. So this is h, and this is going to be way more fun to work with. Now I need to present many equations, which you are already familiar with. But now we're going to use the bracket notation. It's going to be lots of fun, and it's going to make everything very easy. If I would ask you before, what is the mean location when I'm in the energy level 2 and 3, we could be discussing. Now we know exactly how to solve it. When A Degel acts upon n, it gives me a number. It gives me n plus 1, square root of n plus 1 over the state n plus 1. So it brings me up a level. Here it is. When A acts on n, it gives me square root of n times n minus 1. Is this bracket notation okay for you? Okay. Now what happens if I act A Degel A on a certain state n? Of course I need to first act this guy. So it will give me A Degel on, when A acts on n, it gives me square root of n times n minus 1. Now this is now just a number, it's a constant, so I can move it back to here. A Degel on n minus 1. Well, what happens when A Degel acts on state n? It brings it up a level, and it's multiplied by a constant. Which is the constant? The new n then it will reach, right? I can also call it m if it should help you. But one can see that it's going to give me square root of n times square root of n times n, which is m n. Was this clear? Are there any questions on this? Okay. This thing, therefore, is also called the number operator. When it acts on state n of a harmonic oscillator, it just gives me the number itself. Now what happens when h acts on a certain state n? I already know what h is, right? It's h bar omega, A Degel A plus 1/2. So it would be h bar omega, A Degel A plus 1/2 on a state n. This would be h bar omega. When A Degel A acts on n, it gives me n. The half is 1/2, and I remain with n. Now you know that Hn is equal to E on n, which is why this is simply the energy En. So every state has its energy. State number 7 has the energy of 7.5 times h bar omega. Now let's show that that A dagger A is Hermitian. N operator dagger must be equal to an operator itself, right? Therefore, what is N dagger is A dagger A dagger, and doing dagger on each of those, it flips the order and then puts a dagger on each one of those individually. So it's this one dagger times this one dagger dagger, which is A dagger A. Which is N. Lots of boring things here. Actually, no, this one is important. The following relation is going to be very useful. What happens? We already met this thing, right? A dagger. You know that this means A dagger minus A dagger A. Right? This is like XP, etc. What I told you in the past that commutation can be 0. For example, x and x squared, the commutation relations are 0, right? It's x cubed minus x cubed, which is 0. You know that x p is going to give you IH bar. So a commutator can either give you a 0 or a number or an operator. What is going to, we showed this before where Lx and y was something LZ, IH bar or something. I think IH bar, am I right?
I think you are.
Times alpha. Now I'm good. Okay. So what is that going to be? Do you know? Have you seen it?
Yeah, it's 1.
Yeah, it's 1 and it's an important relation because it's very, very useful. Oh, I should not erase this. Whatever. As you know, the way to find the commutator is to have it acted on a certain state. So A dagger minus A dagger A on N. I already know that which of those is the number operator? Ah, this one. So it is like A dagger N minus N, right? Okay. Now when A dagger acts on N, it is like A square root of N plus 1 N minus N, which is when A, let's do it slowly.
It's a plus 1.
Of course. That's what I wrote. So here I just switched the order of these two. I'm allowed to because this is a number. A times N plus 1 minus N. Now when A acts on N plus 1, it brings me down a level, right? But it also gives me a constant. What is this constant? It's the all place. Therefore, square root of N plus 1 times square root of N plus 1 on N minus N. Which gives me N plus 1 minus N on state N, which gives me 1 on state N. Therefore, this is equal to 1. Another commutator that I wish to show you, I won't prove it, but it's very easy to prove just as all the other ones, is N with A dagger is A degel. And n with A is minus A. Okay, now I'm going to finish with one last and long exercise, practicing those operators. You know that in state 0, in time t equals 0, the mean psi is given by the psi of t equals 0 is 1 over square root of 3 times phi1 of x plus phi2 of x plus phi3 of x. The first three states, find x and find x squared. Well, I know exactly how to write x, like A and A dagger are a combination of x and p. But I can also write it the other way around, right? I know that x is square root of h bar over 2m omega times A dagger plus A. Okay, I can even write already now that x squared is going to be, without a square root now, h bar over 2m omega. And I have A dagger times A dagger. I'm going to have A times A. I'm going to have plus A dagger A plus A dagger. Now instead of A dagger, wait a second, which one of those is the, instead of A dagger, I don't like it. This one is a number operator, right? So this one's easy. This one I don't like. Instead of A dagger, I can write I can write 1 plus A dagger. Am I doing A dagger A? Yes. Is this okay? I use this relation here. I isolated this.
Right.
I isolated this, and by moving this to this side.
Is it bigger or
Of course, this was the whole point. Thank you. Okay, now, what I need to do now is a sandwich. Psi, x, psi. And I already know what it's going to be. It's going to be 1 plus 2 plus 3 times, now I'm looking for x, right? So I'm going to use here A dagger plus A. Times 1 plus 2 plus 3. I need to divide all this by 3 because this one has square root of 3 and this one has square root of 3. So altogether I have 1 over 3. And I also need to have it multiplied by square root of h bar over 2m omega. And from here it's going to be easy because assumingly what you have now is 1, 2, 3. I need to multiply this by 3 terms and this by 3 terms, giving me 6 terms. And then I have 3 terms multiplying 6 terms. That's 18 terms. This is horrific. Doing it with direct integrals or even with Hamid polynomials is not fun at all. However, doing it with just bracket without actually solving any integral makes it super easy. Why? Because I'm not going to have so many terms. Let's call this thing here C. Okay? Have your C times. When a digger acts on something, it's going to move it to be 2, 3, and 4. The 4 is going to be irrelevant, right? I'm going to have only a 2 with a 2 with a constant of 2 with a 2 is going to give me a constant of. I'm now working with a digger. So it's going to give me a square root of 2 here, and here is going to give me a square root of 3. All this is coming from a digger. Now, it's this thing and this thing. Now I'm going to have what happens when A acts on those things. When A acts on this, it gives me 0. Does 0 exist? Yes, the 0 level does exist. But it has nothing on this side. Just like the 4 before. Does 4 exist? Yes, but it has nothing on this side because of orthogonality. So this and this is 0. It doesn't give me any. It won't contribute to anything. What I'm going to have is this and this. So, I'm going to have here plus. When it acts on this, it gives me the square root of.
Isn't in the first one the square root of 3 and the square root of 4?
No, when A acts on 1, it gives me the square root of the new state. A digger, sorry. A digger gives me the square root of the new state.
Right.
Okay, now I have here, when it acts on the 2, so I get a 1. I have here 1 times square root of 2 plus 2 times square root of, when it acts on this, it acts on this times square root of 3. So altogether I have here C times square root of 2 plus square root of 3 times 2. And a very specific number. I don't have much more time, as in like -1 minute. But the next thing I would want to show is what happens when I add here time. What would happen if I did the same thing, only now with time? I would have to multiply each of these by a positive exponent, and each of these by a negative exponent. Let's do this times e to the plus I omega 1t times e to the plus I omega 2t, and this times e to the I omega 3t. Here we have e to the minus I omega 1t. Here we have e to the minus I omega 2t. And here we have e to the minus I omega 3t. Well, what would I have now? At this thing, multiplying 2 and the new 2, let's write the answer. I had here altogether 4 terms. It should not be so hard, right? Let's start with the green one. The first thing, I'll fill out the 2. I have square root of 2 coming from this thing, where I had e to the I omega 2t times e to the, this thing came from bringing this up 1, right? So e to the minus I omega 1t. This is multiplication in between. What would be this term? It is square root of 3, and here I have e to the I omega 3 t times e to the minus I omega 2 t coming from this guy. it went up a level because of the integral, but its energy still goes like E2. This exponent. Now I have the red terms coming from A plus this term A acting on 2 with a sandwich on, sorry, A acting on 2, bringing it down to 1, brought me here. So I had e to the I omega 1t times e to the minus I omega 2t times square root of 2. This is what was this before. Plus, now I'm going to have this term with this term. I'm going to have e to the I omega 2t and e to the minus I omega 3.
You must have the inverse of the first term, right? Because if don't, you will have signs, imaginary signs, and the expected value will be imaginary.
Yes, very good. What I want is, of course, cosines. I'm going to have this and this is exactly the same. It's an addition between opposite exponents. It's going to be a cosine. This and this is opposite exponents, so it's going to be another cosine. And altogether, I will get something. What do we get? Oh, and notice that omega 1, 2 is just like omega 2, 3. Like the difference between them. It's just h bar omega. The difference between the energy levels are the same. Altogether, I would get that x of t would be 2 over 3 times h bar over 2 and omega. 2 comes from the fact that this plus this is 2 cosines times square root of 2 plus square root of 3 and cosines of omega t. Where omega is the thing is like square root of k over m of the harmonic oscillator. Thank you very much for listening. I will upload the homework later today, probably tonight.
May I ask you a question about the homework?